Let's get started with lecture 6. Hopefully the sound quality is better. I'm using a new microphone. So last time we talked about, first we defined torque. We had some practice calculating the net torque due to a bunch of forces acting on a rigid body. And then we found the rotational counterpart of Newton's second law. Right, so we found this important equation that the net, let's say, torque acting on an object due to external forces is given by I, the moment of inertia, times alpha, the angular acceleration of that object. And this was the analog of F equal ma for a point particle. Now, so last time I didn't really talk about the proof of this, and I actually had a couple of questions about this, so maybe it's worth it to just briefly mention how this arises from Newton's second law. So imagine, again, we break up our object into a whole bunch of tiny pieces, right? Each of them has some mass. And then, so each piece is experiencing two kinds of forces. There are some external forces that are applied to this object, and there are some interaction forces between different parts of these objects. So more generally, if you have like a collection of particles, let's say, I don't know, you have M1 here, M2, M3, and you have some axis of rotation here. There are some external forces which contribute to this net external torque, and then there are internal forces, action reaction between different pieces of this object. So, and they come in pairs, right? But then if we calculate the torque on every particle, that torque, some of it comes from external forces, some of it comes from these internal forces. However, if we add all the torques on all the particles to get the total net torque, we see that the internal forces don't contribute because they come in these pairs, like they act along the same line. They have equal magnitude, opposite direction. So if I calculate the torques of these two forces as an example around this axis, well, this is the arm of the rotation. The torque of this force is clockwise, this magnitude times the length of that arm. The torque of this force is counterclockwise, again, the same magnitude times the same arm. So they go away, so we can forget about those. So we can only think about external forces. Now, let's think about external forces acting on these particles. Again, let me focus on one of them, M3. And the net external force acting on M3, let's call it F3, right? Here is my axis. Here is the arm to where the particle is. Now, that torque, that force rather, has a component in the direction of the arm and has a component perpendicular to it, right? So if I decompose my external force acting on one of these masses along the arm of rotation connecting the mass to the axis and the perpendicular direction, I get these two. So the one that's in the direction of the arm doesn't contribute to the force because it makes an angle 0 with the arm of rotation, and then the one that's perpendicular is giving me a torque equal to, so let's call this the perpendicular, let's call it F3 perpendicular, right? And let's call this one F3 parallel. So the one that's parallel doesn't give me any torque. The one that's perpendicular will give me a torque equal to, let's call this distance R3 times F perpendicular 3. Now, if I consider the acceleration of this object, I can apply F equal ma, and it has some acceleration, some centripetal acceleration in the direction of this line connecting the axis to the particle, and some acceleration perpendicular to it, or tangent to a circle you can imagine. Right? So if I take this acceleration that's tangent to the circle, the tangential acceleration, let's call it A perpendicular, that's going to be the force divided by mass. Right? They're both in the same direction. Okay? Now if you have a tangential acceleration in your circular motion, again, in the same way that angular velocity and velocity were related by a factor of radius, this tangential acceleration is just a rate of change of the tangential velocity. So it's related in the same way to alpha, to the angular acceleration. So I can write it as the distance, the same distance times alpha. So let me put all of these together just for this one particle, particle 3. What do I get? Well, we get tau 3 is R3 times F perpendicular, which I can write as M3 A3 tangential, perpendicular to the radius. And that's R3 M3 A3 is again R3 times alpha. So that becomes R3 squared M3 alpha. That was for one of the particles. And you already noticed the same combination, distance squared times mass. And then all the particles, if they belong to a rigid object, they have the same angular acceleration. So if I add all of them, so net torque will be sum over I, let's say I labeled my particles tau I, and that's equal to sum over I Ri squared Mi alpha. And this quantity, that sum, if I factor out alpha, which doesn't depend on which piece I'm considering, if I'm thinking about a rigid body where all the distances are the same, is just the moment of inertia around that axis. So tau equal I alpha is not a new kind of fundamental equation. It's just if you think of a rigid object as many tiny point particles and you apply F equal ma to all of them, all of those equations reduce to this because of this very restrictive constraint that they all have the same distance from each other. That the object is rigid. All right. So again, as I said, you can skip over this derivation, but I think it was maybe worth it to spend 10 minutes showing this. So we don't think of it as a new kind of fundamental equation, right? Newton's second law, F equal ma, is a fundamental law of nature. Tau equal I alpha is not a separate thing. It follows from Newton's second law. So kind of I, the moment of inertia, and an angular acceleration, angular velocity, these things were defined in a way so that they serve as counterparts of mass and force and velocity and acceleration. All right, so that's our main equation that we derived now and we mentioned last time. Then we did some work on, again, constraints on masses and pulleys when you have ropes that kind of don't slip with respect to pulleys. So we found, again, if you have a pulley and you have a rope around it, and maybe there's some object here. Okay, the rope on the other side does whatever. Maybe there's another object, or it does something. So this object here, we found that its acceleration is the same as the acceleration of a piece of rope over here, right? Because the length of the rope doesn't change, the rope doesn't stretch or compress. So if this object comes down by some distance, this little piece that's a length L rope above it comes down by the same distance, and then all the derivatives are also the same. So the velocities, the accelerations will be the same. And also, so let's call this a rope. And also on this point, the point of contact on the pulley, if there is no slipping, we have the same downward acceleration because there is no relative motion. At that point, the pulley and the rope are moving together. So let's call that a pulley at this point here. And this is again the downward acceleration of this little piece over here, that belongs to the rope. So for the pulley, because it's just rotating around its center axis, we can say a pulley is r times alpha, the radius, times the angular acceleration. And then, of course, this is equal to a rope is equal to a object. And the same goes for velocity. So these are important constraints that allow us to make progress on solving these problems. So that's one equation. And the other equation is the velocity of the object is r times omega. Okay, so we talked about these things last time. So today, the first topic I would like to talk about is a very special case where an object is in static equilibrium. It doesn't move, it's stable. It's just sitting somewhere. So that implies two things, right? If it's not moving, first, its center of mass is not moving. The center of mass is one point belonging to this object. It's not moving. It means the center of mass has zero acceleration. Remember, we argued that the net external force is sum of all the forces acting on an object added as vectors is equal to the total mass times the acceleration of the center of mass. So if the center of mass is not moving, which is a consequence of the object not moving, then there should be no net force acting on the object. Furthermore, if it's not moving, it's not rotating, and it cannot have angular acceleration. So we just showed that the net torque is equal to the moment of inertia times the angular acceleration. So if there is zero angular acceleration, there is no net torque. And these two are the conditions for static equilibrium. And that's, of course, a whole branch of engineering. All the structures buildings, bridges, all kind of civil and structural engineering, dams, all of them, use these two constraints to analyze the structures and think about whether they would fail or whether they will be stable. This is, of course, also put together with some geometric constraints about kind of how things stretch or how they compress, and they should be consistent if things are connected. So there's, of course, a lot more to structural engineering than statics, but statics is certainly step one. Okay, so what we want to do is to get some practice, right, in various problems where you have a rigid body in static equilibrium, and we want to use that to find maybe some unknown torques or find some quantities. We want to analyze this problem. So it's kind of baby statics, a simple version of statics. Okay. So as I mentioned, when we're doing statics, we have two equations. Sum of all the forces is zero, sum of all the torques is zero. If we're looking at a two-dimensional problem like this, so it's not in three-dimensional space, so basically the object can fit on a two-dimensional plane, and there's one axis of rotation. It can basically rotate in plane, so the axis of rotation is going to be perpendicular to the plane. Then we get one equation that the net torque is zero and the net force is zero. This is a vector equation, right? So that's, for a two-dimensional problem like this, implies two equations, one for the x direction, one for the y direction. Now, so there's no ambiguity about this equation, the force equation. However, the torque we defined with respect to an axis. So when we say the net torque is zero, and there is no obvious axis of rotation, the question is with respect to which axis, right? So what I want to show is that if the net force is zero, and the net torque is zero with respect to any axis, it will be zero with respect to all other parallel axes, okay? So it really doesn't matter. We can pick a convenient axis or pivot point, find the torque around that, and if it's zero and the net force is zero, then we're guaranteed to find a zero torque around any other axis. Okay, so let's go back to the notes and try to make sense of this. All right, so instead of a general proof, which can be done but may not be very illuminating, let's consider an example. So let me consider a simple case. You have just a rod, and there's a pivot here, for example, and then you apply, let's say, a force F here downward. Here you have a distance L, and let's say a distance L over 2, we apply a downward force 2F, and then at the pivot point, if the net force is 0, right, we have a force 3F down, so we must have a force of 3F upward. So therefore the net force acting on this rod is +3 - 2 - 1, which is 0. And you can see that around this pivot point, the net torque is 0, right? Because this one, the force of 3F that goes through the pivot, gives me 0 torque. This gives me a torque that's counterclockwise. FL is the magnitude. This one will give me sorry, that's clockwise, right? It wants to rotate this way. That's, yeah, it's clockwise here. I mean, the figure was right. This one wants to rotate around that pivot point this way, so that's counterclockwise. It wants to rotate this object like this, right? This force is pushing down this point, so it wants to make the object like that. This one is pushing this end down, so it wants to rotate this way. And this is a clockwise rotation for this force. Here, I have a counterclockwise, right? This end is going up. Okay. So this is an example. You have three forces. They add up to 0. The vectorial sum of all these forces is 0. And their net torque around that point is 0. All right. So now let me say I don't know if there's something natural about that pivot point. I know it's in static equilibrium. I just have three forces. Who says I have to take the torque around that one point? I mean, the claim is if you don't have an axis there, if it's not kind of pivoted there, you just apply these forces at those points. Right? These are three forces whose net force is 0, and their net torque around this point at least is 0. So this object, if you just have it in free space and apply those three forces to it, it shouldn't have any center of mass acceleration or any angular acceleration. Okay. Now, what if I wanted to calculate the torque around a different axis that's a distance r away? I move it that way. Well, what would I get? So what is the torque that I would get? So let's do that. So tau. All right. So for this one, I have a force downward. The distance now from this axis is going to be L minus R, right? So I'm going to get minus F because it's clockwise times L minus R. What about this force here? Now it doesn't give me a 0 torque. It's at a distance r from the axis of rotation, and it wants to generate again a clockwise rotation like this with respect to that axis. So again, minus F times R. Minus 3F, right? The magnitude of the force is 3F. This one, with respect to that axis, wants to generate a counterclockwise rotation. So I'm going to get plus 2F times, here I have L over 2, here I have R. So this distance from here to here is L over 2 plus R. Okay. So I'm going to get minus FL plus FL, right? If R is equal to 0 from this term and that term, the terms that don't have an R, the two axes are the same. I find the torque with respect to the original axis, and that was 0. Now, what's the change in the torque? So I now put together the terms that have an R. I factor out my R. If I factor out the R, from this term I have minus times minus, that's an F. From this term I have minus 3F. From this term I have plus 2F. So that's just the sum of these forces, and we know that's 0. So I get 0. So this is more general than this. I mean, you can have some axis and you have a bunch of forces acting at various locations with different magnitudes, and you can find the net, but somehow they all vectorially add up to 0. and you find the net torque of all of them around this axis, they add up to 0, then you can take an arbitrary axis somewhere else, so axis 1, axis 2, and one can show that given that the net force is 0 and the net torque is 0 around one axis, then the net torque is guaranteed to be 0 around any other axis. So that's a special case where we showed this. All right. So therefore, the lesson is that to analyze the static equilibrium, we have this freedom. When we write the equation that the net torque is 0, we have complete freedom to choose whatever axis we want. And it's oftentimes convenient to choose an axis that gives us kind of simpler equation, because that way we're going to do less algebra, right? So if you have a point where you have a lot of forces there, right, sometimes it pays to pick the axis over there, so those lots of forces that go through that point give us 0 torque, and then we get shorter equations. Okay. Yeah, so that's a very good example. So I'm going to read through this to make sure we're on the same page regarding what the problem is asking, and then I'll ask you to pause the video and work through this problem on your own, and then we come back and go through the solution together. So we have a ladder. We know the length L. So in this case, it's 3 meters, but we're going to try and solve this problem algebraically in terms of L. It leans against a frictionless wall, so there is no friction over here at the point of contact between the ladder and the vertical wall. And the angle between the ladder and the ground is 60 degrees. So that angle over here is 60 degrees. Okay. The question is, what is the minimum value mu s, the coefficient of static friction, with the ground that prevents the ladder from slipping? Okay. So this is our ladder. We can think of it as having uniform density, so its center of mass is right in the middle. And it's leaning against the wall. There's no friction there at the wall. There is some friction on the ground. So we want to see how much friction do we need to prevent this ladder from slipping, right? If there's no friction, right, what's going to stop it? This end is going to just slide down and move here, and this end is going to come down. So we need friction for the ladder to stay put against the wall, but we want to find the minimum required value of mu s, so this happens. So this is example 12-15. Okay, so let's draw this again. This is the frictionless wall. This is our ladder. Of length L. Here, that angle is 60 degrees. Let's call that alpha. That's L. Now, then we draw a rigid body diagram, right, for this ladder. Okay, so what are the forces? Well, we know that there is no friction between the ladder and the wall, so there's only one force, let's call it N2, normal, perpendicular to the wall going this way. There's going to be a normal force from the ground, let's call it N1. There's going to be friction force, let's call it Fs, for static equilibrium. So those are the only two places of contact, right? The ladder is in contact with the wall and the ground. We know there's no friction at the wall, so the force is only normal. And then there's the weight, gravity, let's say mg. And we discussed this before. So whenever we have a rigid body and we can consider the total force from gravity to be applied to be equal to the total mass times g applied at the center of mass of the object. All right, so I know I have two fundamental equations, right? One is sum over F is 0, another is sum over torques is 0. If it's in static equilibrium. So the net force, well, I can pick a coordinate system, right, and consider consider like the x component of that equation and the y component of that equation separately. So this really is shorthand for two equations. Sum fx is 0 and sum fy is 0. Okay, so if I consider fx, two of these forces are already in the x direction, so that gives me n2 minus fs is 0. So n2 is equal to fs. That's one equation. Let me write it here so we keep track of where it's coming from. For the y direction, I have two forces in the vertical direction. So what I find is that n1 is equal to mg. Okay, so those were two straightforward equations. Now I want to write my torque equation, right? So I can pick some point around which to write the net torque. And that's my choice. I have freedom what point to choose. So I see that here at the bottom, there are two forces that already go through there. So if I write my torque equation around that point, I get an equation that only has two of these forces. Only n2 and mg appear in my torque equation. So that seems to be the simplest way. Again, you're going to completely solve the problem correctly if you write it around any other point. I mean, you can write it around the contact with the wall, so only n2 disappears. You can write it around this point where mg disappears. If you really want to take the long way, you can write it around some arbitrary point in the plane. But I mean, that makes the calculations, of course, lengthier unnecessarily. So yeah, so let's write the most convenient equation for us. Okay, so let me draw this again here. So mg, let's first focus on this force. From here to here, what distance do I have? The length of the ladder is L. It's at the center of mass, so in the middle, so that length must be L over 2. This angle we called alpha. So I'm writing the torque around this axis here. It's going to be a counterclockwise torque around this axis. It wants to rotate it this way. And to find the magnitude, well, I can find this this length here, right, perpendicular to the force from the axis. And that is going to be, if I look in this triangle here, so the hypotenuse is L over 2, this is adjacent to angle alpha, so I know cosine alpha is, let's call that, I don't know, R, if you wish, R over L over 2. Therefore, R becomes L over 2 cosine alpha. And this torque that I get, let's call it tau m due to the mass, is L over 2 cosine alpha. All right. Now, what about this one? So it is applied here. Let me draw a second picture so it's not too cluttered. So again, this is the axis I picked. This is the ladder. I focus on this force N2 over here. And you can imagine like the distance from the axis to the line along the force. So this is the distance I need, right? And well, how do I find it? If this is alpha, then this is alpha here. Well, this length is equal to that. So you can see it's in this big triangle with hypotenuse L is opposite alpha. So this length from here to here is going to be L times sine alpha. So I find the torque, and let's see what's the direction it wants to rotate around that pivot point. It wants to rotate the object this way, right? Clockwise. So this is clockwise, that's counterclockwise. That's good, their sum can be 0. So tau N2 becomes L sine alpha times, sorry, here tau m was L over 2 cosine alpha, that's the distance, times, of course, mg. And this is times N2. Okay. So after all this trigonometry, we can write that if the net torque is 0, you know, let's write the counterclockwise with a positive sign, L over 2 cosine alpha mg. And then we write the clockwise with a negative sign, so that's minus L sine alpha N2, that's 0. So we collected all the information we could from our equations, right? From the net force and the net torque being equal to 0. So let's stop and think for a few seconds about what is it that we're after. We're after the coefficient of static friction here. And that has to do with the ratio of the friction force to N1, right? The normal force at the point of contact with the ground. So somehow, if I'm interested in mu, in the coefficient of static friction, I don't care that much about mg. I don't care that much about N2, right? So what I care about is Fs and N1. And you can immediately see that we can, because these two equations, the force equation, the force equations are very simple, we can immediately eliminate mg and N2, right? So let's write this equation here as L over 2 cosine alpha, mg is equal to N1, I just plug it in, is equal to L sine alpha, N2 is equal to Fs. So therefore, I find the ratio of Fs to N1, right? You divide both sides by N1 and then by L sine alpha. So on this side I get Fs over N1, on this side I get, the L's go away, I get 1/2 cosine alpha over sine alpha. Okay. So if this ladder is in static equilibrium, it's not slipping, the friction force must be N1 times that number. Cotangent alpha over 2, right? And we know that for a given normal force, if there's no slipping, the maximum friction force that we can have is N1 times the coefficient of static friction. So in order to support this, right, we must have the minimum mu s to be equal to cotangent alpha over 2, right? Because if you have a smaller mu s than cotangent alpha over 2, the maximum fs you can get is going to be smaller than that, than n1 cotangent alpha over 2, and we cannot satisfy this requirement of static equilibrium. So we're done. So from here we find the minimum mu s is just equal to that, cotangent alpha over 2. Alpha was 60 degrees, so I guess cosine of 60 degrees is 1/2, right? Sine is square root 3 over 2. So I think cotangent 60 is 1 over square root 3. Yeah, that makes sense. So yeah, therefore minimum of mu s is equal to 1 over 2 square root 3 for this particular angle. So interestingly, it doesn't depend on mass, it doesn't depend on length, it only depends on angle. That's at some level expected, right? Because the coefficient of static friction is dimensionless, right? It's the ratio of two forces. So something dimensionless, if there's only one length scale, L, there's no other length. And there's only one mass scale, M, there's no other mass in the problem. Cannot depend on any of them. It only depends on the angle. Because with one mass, we cannot make a dimensionless quantity. We need to have at least two different masses, so the ratio, for example, provides a massless quantity. All right, here's a quick question for you. So take a look at it, pause the video, try to figure out the correct answer, and then we'll come back and go through it together. All right, so what was your answer? Well, what is the question? So which object is in static equilibrium? Okay, so let's go through them one by one and examine each. I think even the ones that are not in equilibrium, it's helpful to understand why not. So A, well, we have two requirements, like both of them must be satisfied. One is the net force is equal to 0. So for A, we see that these three forces seem to have the same length, the same magnitude. So you have two of them going this way, one of them going that way. So clearly this cancels with this, and maybe one of them going to the right remains. So there's net force on this, and the center of mass will accelerate to the right. So that cannot be in equilibrium. Similarly, the second one, who cares where they're applied, right? As far as some F is concerned, the positions where the forces are applied doesn't matter. It matters when we calculate torques, but for forces, again, we have two going this way, one that way. That implies the center of mass, oops, I jumped the gun. The center of mass will accelerate to the right. Now C is an interesting case. So we have two forces of equal magnitude going from left to right, but there is one force that looks twice as big, and it goes from right to left. So the net force seems to be 0. Okay, that's good. Now, what about the net torque? Can it be 0? So let me go back to the notes and just take a closer look at this. So we have a square-shaped block like this. There is one force here, one force here, one force that's twice as big here. Okay, so what is the easiest way to calculate the net torque? I mean, we have this freedom, right, of picking our axis. Can you see if I pick the axis anywhere on this line here, where both of those forces are through that? Let's say, for example, I pick this point. Well, the arm of rotation will be 0, because if you draw a perpendicular line from the axis of rotation to the line along the forces, you have a 0 distance. So these two forces do not contribute to the net torque around this axis, right? Or any other axis you pick on this line here. This one will contribute, again, I draw, it doesn't even have to be in the corner, let's say my axis is here. I draw a line perpendicular from the axis to the line where the force is. So this will give me a counterclockwise torque, and if this from here to here is L, and this is F, the torque is FL, right? So can't be 0. That's one choice, right? We said we have this freedom. So if I didn't notice this, maybe I pick a point here as my axis. Again, now we have two forces, so this will not give a torque, this will give a torque. This will give twice that torque, because this line that I draw from the axis to the line where these forces are has the same length for both of them. This is a bigger force, so it will give me a net torque this way. Okay. So if there is a correct answer, it has to be D. So let's see why D works. Again, the net force is 0, right? You have F plus F from left to right, and you have 2F from right to left, so the net force is 0. Let's examine D in a bit more detail here. So it's just the same thing. So these forces are the same here and here. But this other force is applied in the middle. So now, if you take, for example, your axis to be here, you see that one, the 2F doesn't give any torque because this goes through that axis. Now, around this axis, these two distances are the same. This is going through the middle. This will give me a clockwise torque. This will give me a counterclockwise torque, right? So the way to visualize this, again, like you imagine there's some axis going through there, and what is the tendency of this force to rotate my object, right? So axis here, force. It wants to rotate this arm this way. So we can assign those directions, and we see they cancel out and they have equal magnitude. Yeah, so you could have done it differently. So if you just, let's say, you go and you put your axis here, well, this gives me 0. This gives me a torque this way, that's, if that distance is L, is F times L. Here the force is 2F. This distance is L over 2, twice the distance, twice the force, half the distance. Again, it gives me 2F times L over 2, which is FL, in the opposite direction. So it doesn't matter where you pick your axis, you're going to find 0 torque. So indeed, D is the correct answer here. All right, that's a good place to stop. So today we mainly talked about static equilibrium and practiced a little bit applying these two fundamental equations of static equilibrium.